Temperatures seem like a relative scale at heart. You can be hotter or colder than something else. So how do we measure a relative scale? Temperature is measured on a scale that only gives us magnitude. There's no direction associated with temperature. Temperatures go up or down. Celsius is measured between the triple point and the boiling point of water. Triple point is where you can adjust the pressure so that water can be both solid, or all three, solid, liquid and gas at the same temperature. And it plots it to the boiling point of water. Fahrenheit is measured between ice at 32 degrees and boiling point at 212 degrees. Both of these are scales. They are measured between two arbitrary points that people decide and are divided by an arbitrary amount. Again, an amount people decide. You or I could develop a method of measuring temperature that meant something to us. We could say that the temperature at which a car engine idles is the bottom of our scale, and the temperature at which it has its maximum revolution is the top of our scale. Let's choose pi intervals between these points to make the scale seem a little bit more scientific, and let's call it the traffic jam scale. You can measure whatever you like with it. The point is that temperature scales we already have are arbitrary. They don't contain a fundamental aspect of physics. What we need is a fundamental scale of temperature, one that no matter where you are in the universe has a measure in it which is always true. And for that, we need to have a bottom or a top to our temperature scale. From what we know about temperature, it would seem possible to have an absolute zero of temperature. Temperature is the average heat energy per particle in a material. If this heat energy were completely removed from the particles, then this would be the lowest temperature that a material could reach. In effect, all the particles within the material would stop vibrating and moving around. However, how do we know what the value of absolute zero is? The answer comes from Charles' law. Charles' law tells us that increasing temperature increases the volume of a fixed amount of gas. If we plot temperature against volume for different gases, then these different gases would all have different gradients, all linear graphs, but with different gradients. We work backwards along all these different gradients, decreasing the temperature, decreasing the volume, and it would show us that all these gases converge at a single point, around minus 273 degrees Celsius. This is a temperature on the Celsius scale that we call absolute zero, because all these gases converge, and it shows us this is the point at which all these particles stop vibrating. It is the basis of the Kelvin measure of temperature. Unlike the scales described above, Kelvin measurements are not a scale. They aren't between two arbitrary points. They are a measuring tool starting at absolute zero and proceeding up to infinity, with increments the same as the Celsius scale. The problem with Kelvin is that it is too big at everyday temperatures. Water thaws at 273 Kelvin. It boils at 373 Kelvin. Room temperature is about 300 Kelvin. These temperatures are too big, and so we tend to still use Celsius for most of the science we do at or around room temperature.